I think I want to tell the Zoom people that they should have the interface when they're presenting and then have the chat and the participant. Like, it's ridiculous. Why is it all the way? Anyway, it's very annoying. Okay. We got everybody, more or less? Okay. All right. I see more than 50%. Okay. Welcome back, everyone. So yeah, back to our nano story so far, which is here, right? So again, today we're focusing on day 3. So we need all these special tools to make and see things. So yesterday we kind of went through these model activities on how to make stuff. And then tomorrow I'm going to actually talk about some of the activities that we did not get to because a lot of them were just ridiculous to send. So I said, I'm not going to send these, or unsafe to send. So I also said, I'm not going to send these. So that was sort of the whole gist. But I'll go over a few other activities that you can kind of have in your toolkit if you so choose to use them. And I'm happy to sort of set aside some time if you want to go over them for your classroom too as well. Okay. So again, Dennis sort of gave you a broad overview of something that's really complex, really abstract, but he also showed you how to characterize it and simulate, which I thought was a really good sort of bridge, an additional kind of piece of information to this nanoscience puzzle that we have here, right? So a lot of materials are really expensive, really hard to find, or just, they're hard to set up experimentally. So he uses simulations, which I think is really interesting. But then he also uses some of those simulations to actually understand his data and what that data should look like. So it's kind of merging a lot of different fields at once, right? So it's literally hardware engineering, but it's also computer engineering. It's some virtual stuff as well, almost, right, with the simulation. So a lot of things at once. So again, a lot of the science that we're moving towards or developing is very interdisciplinary, which I think is very cool. But now done with that tangent, right? How do we see at the nanoscale? So this is a really cool image here. Does anyone have any guesses on what this is?
Hair. I think it's hair.
There we go. Hair. Okay, so many people. Everyone got it in one. Okay, so you've been around the block. So yeah, this is hair, but then on top is actually a nanowire, right? So think about your hair. It's this. I always look at my hair, I'm like, wow, because you envision, you kind of extrapolate and look at how small that hair is and then how small that nanowire is on that hair. And then how do we generate this image? And Dennis did a quick overview on the SEM that we were looking at, but there are way more pieces or parts to that puzzle, right? So how small can we ourselves see, right? So then visible light is around 400 to 800 nanometers. And we can only see about 0.1 millimeters to the naked eye, and that's usually the approximate of like a period on a piece of paper or like a grain of sand. And then with your light microscopes, so typically in your classrooms, maybe you have a light microscope, and that you can generally see down to like 500 nanometers. And then this is just a reminder of, what sizes we're kind of talking about. So, and then, right, visible light is around 400. This is 700. It's usually 750, but kind of a scale. All right. So what do we do when we're trying to look at something under 5 nanometers, right? Or I mean 500 nanometers. We have to switch. So a big component is this whole nano tool development. Like there's a lot of history, right? And I think thinking back to day 1, right, we had that sword of Damascus, the sword of Damascus and the Lycurgus cup, right? So both of those things, they all had nanotechnology in them, but we didn't know about them. And they're ancient. They're hundreds, maybe thousands of years old, but we just didn't really know what was going on. And so a big part is these tools that we can use to fabricate, study, and control matter at the nanoscale, right? Does anyone know about Richard Feynman? He's a quite famous physicist, chemist, lecturer, science educator. He has, and this is sort of this like, I guess it's Bible is the wrong word, but sort of like hallmark talk that really set forth this whole nanoscience field, I would say. It was this talk. He said, there's plenty of room at the bottom at Caltech. He was a professor there. He has lived himself a very interesting life. He has written a few books. Surely you're joking, Mr. Feynman, and there's another one that I cannot remember right now. But he has written two books, which I'll look up later, and they're both really good reads as well. But anyway, long story short, this is a big, really famous talk where it really exploded things, and he also set forth a bunch of challenges. So he offered in like the 1960s, which I think back then was $1,000 is a lot of money. Now it's like maybe your rent, probably less than your rent. Anyway, $1,000 challenge to take the information on the page of a book and put it on an area 1/25th. I can never say this correctly. 1/25,000th smaller than in the linear scale. So basically, shrinking it down 25,000 times, right? And at that point, a lot of tools hadn't been developed. They were trying to figure that out. And so a big part of this also was in this lecture. I am not afraid to consider the final question as to whether ultimately in the great future we can arrange the atoms the way we want, the very atoms all the way down. And we actually have tools that we can use to actually place individual atoms. That's where they developed. And this actually won a Nobel Prize. And it was a collaboration between Stanford and IBM. Calvin Quate, he was a professor and also I think some senior fellow at IBM. They invented this tool. It's called the atomic force microscope, also known as the scanning probe microscope, which you're actually going to see later today with one of our colleagues, Marcin. But it's a way to take a really sharp tip, get it really close, and you can actually sort of feel bumps, like feel the force of bumps of materials at the atomic scale. So it's really cool to experience. And okay, so 26 years later, right, 1959 is when they posed this question. And obviously we have to represent Stanford, but actually Stanford won this prize. Stanford won this Feynman Prize, which I think is really cool. And so the Stanford grad student Tom Newman claimed that $1,000 by using an electron beam. So using a beam of electrons to write on the surface of a piece of plastic, actually, the whole first page of The Tale of Two Cities. And so it's a picture of him. This building still exists. The person who actually took this image still works at Stanford. Her name is Ann Marshall. She's retiring this year, but she's amazing. I asked her about it, and I actually met the professor who is, overseeing this student. His name is Fabian Pease, and he's actually trying to create an SEM that is cheap, like a cheap SEM that is less than $1,000. So I think that's also really cool to be at Stanford and have all these really cool people working together. But anyway, long story short, they did this. There's a story they actually had to send this information by telegram, right? That was in the 60s or 80s, but they sent it by telegram, I believe, or something, to actually get the information, because I think he was overseas, something ridiculous. But anyway, and then they mailed this because they didn't have email. So all sorts of things. We've come so far. Okay. And then what is this? About 4 years later, then they were also able to write with the atoms, right? So I think maybe some of you might have read that in your NanoSIMST yesterday. I forget which issue it was, but so this is a big part of the story where they were able to use that microscope, the atomic force microscope, to pick up atoms and then drop them and place them wherever they want. So this is the actual image. It's an atomic force microscope image of xenon atoms, which are much bigger, plopped onto a background of copper atoms to spell out IBM. They obviously did it at IBM, so they had to represent their logo. Oh, thank you, Samantha, issue 11. So yeah, they were able to do that. And you can actually see sort of, it's actually just a contrast thing, right? So you see the big blobs of xenon atoms, and xenon, if you look at the periodic table, is much bigger. It's further down and to the right than copper. So you'll see the copper little like round dots, but it's a little bit harder to see in comparison to the xenon atoms. And then another thing, and then fast forward, what is that? Hold on. 89 to 13, 13 plus 11. 13 plus 11 is 24 years later. They did the world's smallest movie. So I won't go into it in too much detail, but they did a stop motion video of a atomic, basically stop motion video, which I thought was super cool. So they used that microscope that I was talking about to pick up atoms and place them, and then basically take pictures over and over again to make a cute little video on the movement of an atom. So I won't, well, let's see. It's really cool. But
Angela, just a quick question now. When they put the xenon atom on the plate, any binding happen, or just the atom just sat on that plate?
I believe it just sits on top. There is no actual binding, but generally speaking, there are sort of some forces at play that usually want to stick together, like van der Waals forces and things like that. So they won't just like float away. It's kind of like almost like the Cheerio effect, where all the Cheerios like to kind of clump together.
Okay.
Yeah. But yeah, I think this is really cool. I think he plays soccer. He kicks it eventually. But yeah, so these were thousands of carbon monoxide molecules. I'm not sure what the background is, what the substrate is. But yeah, these are crazy. This is crazy. They're moving molecules and taking pictures of them. So, and then what's really cool is, so this is the actual video, but then they also go into, which is a much longer video, how the video was actually made. So it's a really nice thing, and you could, plan a lesson around it as well. Oh, Samantha says issue 12. Never mind. Okay. All right. And then this is just to give you an overview of light versus electron microscope. So a light microscope, generally, most people are familiar with, correct? If not, it's really just moving light through a series of lenses, and then enlarging the image, and putting the light through the lenses, and then you would look at it, right? Whereas with when we have to switch over, because light is too big, right? The limit is about 500 nanometers. We have to then switch over to electrons, because electrons, their wavelengths are much smaller, so we can probe things that are much smaller. Okay, so there are generally two different types of electron microscopes that are the most popular. One is called the transmission electron microscope. You can see it here. And we abbreviate everything, unfortunately, but it's called TEM, transmission electron microscope. So in this case, you're sending your electron beam through the sample, and then you're looking at it at the end. Okay. Whereas a scanning electron microscope, a scanning electron microscope, you have the same electron beam, right? And actually, another interesting thing when it comes to electron microscopes is, in order to manipulate the beam, you're not using lenses anymore. Or you're using lenses, but they're not made out of glass. They're actually made out of magnets. Because electron beams can be changed by magnets because they're influenced by magnetic force. So the lenses are actually made out of magnets. And anyway, so with the scanning electron microscope, it does this. It does exactly what it says. So it scans. So it goes across the surface of your sample, and then you measure the electrons that bounce off of the surface. All right. So TEM, the electrons go through the sample, so you kind of just see a cross section. Whereas the scanning electron microscope, you just see what kind of bounces off. All right. And so going back to day one. This is just comparing between the light microscope and the electron microscope, but this on the right side is what a scanning electron microscope image would do, right? So you can see the image, you might envision the electrons bouncing off, and the image that it creates almost kind of pops out at you. It looks very 3D, right? Whereas a transmission electron microscope would look more like the optical microscope, where it's more of a cross section, okay? So it's just a thin layer of what's going on, because the electrons are going through your sample, not bouncing off of your sample. So again, SEM, it's more like a topographic, whereas TEM, it's more like a cross section, all right? Okay, and again, this is just one example. There are many examples. So what we're gonna do is we're gonna do a mini little quick activity. So I sent you a bunch of these magnets. I don't know if you saw, a whole stack. So you're gonna grab those. Yeah, no, on the last slide, it was an SEM image and a optical microscope. I will show you a TM image later. Yeah, thank you. So you're gonna grab this magnet. It's a really simple activity. I do it with kids of all ages. So you're gonna be tasked with a job to take your probe off. So before it was attached like this, right? Until you'll rip it off. So you'll have the two pieces. Okay, and what you're gonna do is try to figure out what the structure of this sample is. Okay, so just for the sake of time, I'm going to give you a hint, which is try using the backside and use your probe. This is your probe. This is your measuring tool to figure out what the sample structure is. Okay? And so you have 4 options, A, B, C, or D. So you guys can maybe put it in the chat and figure out which one it is. Or when you have an answer, figure it out. Does anyone feel anything? C, D, okay. No one thinks it's A? B, okay. And so make sure to go in different directions so you really decide, gather all your data, basically. B, okay. B's, D's. I feel something. What is that? Well, what happened on day 1? What do we remember about magnets? Okay, B. We got a lot of B's and D's. Okay. Oh, you might have different ones. Oh, interesting. I hope not. They should all be the same. All right. Does anyone want to explain their answer at all? Does anyone want to volunteer as tribute?
I don't know if I'll explain this correctly,
No worries.
but when I took I guess you guys should see me. So when I took this and went across, I felt that clicking. Just you could feel it tugging just a little bit, and then I turned it over and did it again, but I felt like there's a lot of clickings. So I felt like after you turn it over, it's C, because there's a lot of click, 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 click going across.
Okay, so you felt it going both ways. Is that what you're saying?
So always going this way, but it depends on if I lift it this way or this way.
Okay.
So if the key was up here or if the key was down there, I would feel something different.
Okay.
But I don't know.
All right, thank you. Yeah, that's a good observation. I do feel the clicking. Anybody else? Anybody disagree or agree?
I only feel it this way.
Okay, so yeah, you
go straight across.
Yeah, if you go straight across.
I think it's B. If I pull down, I can hear it click.
Yeah. Well, okay, Yanette, good point. You thought these were refrigerator magnets for the students. They are. They serve 2 purposes. I tricked you. Okay, so not really, but Okay, so the answer is actually D. I think it's so much harder to do this, you know, because we're all remote, so I can only show you what's going on and it's a mirrored video, but okay, I'll try to get close and show you. But you go like this, right? And you feel the bumpiness, but if you go like this, do you feel any bumps or is it smooth? Okay, it's quite smooth. So we can for sure, no one picked A, so that was definitely an option, a no. But then B, do you feel it going, you know, the hot dog way or the hamburger way? You remember that? That's how I remember.
Are there different ones? Seriously?
No, they should all be the same. If they're not the same, I'll be very upset.
Watch. Smooth, smooth, right? But then when I go this way,
Oh my gosh, maybe you got printed differently.
yeah, look, can you hear the clicking?
Yeah.
Yeah, so
Huh.
mine is if I put it this way,
Oh no.
the answer is B. See, it's here now. Look at this one. Click, 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 click.
Yeah.
It's the way that she's dragging it, though.
You
It's
think so?
the direction. It's the way that the way you're orienting that little piece across the bigger piece. You change the orientation.
No, but if you go like, it should go like this, right? Because the magnet got pulled off of here, so it should be the same piece.
But look at how she's dragging it, though. She's dragging it differently.
You don't feel any bumps, Vicky? Well, Vicky,
No,
what
it's smooth. Look, smooth.
can you hold
Now look
it
at this way.
maybe like when it's like a, do you still feel the bumps this way? If
Can you see my hand? Now,
yeah, this way should be smooth, but if you go this way, is it bumpy?
no, it's totally smooth. Now listen.
Yeah, yours is different, I think, to be honest with you.
Let me look at another one.
Can you show me the front of your magnet? Is it the same? I did have new magnets printed, but okay. All right, well, this is not great. Okay, well, it's supposed to be D, but now I'm a little worried. Maybe we got sent different magnets. Okay, yeah, and Dustin has the same. Oh no,
This
okay.
one is D,
Okay, so yeah, that one is D. Okay.
but this one's B.
Oh man.
That's cool. I think it's cool.
Oh no. Well, okay. Don't tell the kids. Let them figure it out.
How would you simulate C?
See, I think you would have bumps on. You would have to not move the probe, and it would go bloop 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 like and do the vibration this way. But then if you went this way as well, it would also do the vibration, the bloop bloop. That's a horrible sound effect, but you know what I mean. Yeah. Okay.
These are
Yeah,
cool.
it's okay if there's both. Wow, that's never happened. I wonder how that happened. Okay. Anyway, so this whole point, the end of the story is this is actually to simulate one, nanoscience properties, right? Where again, we're using these magnets as a model to say, hey, you cannot see, but you can feel using your special tool, right? That's one aspect of this piece of information. And then the second part is, how exactly does this work? So the magnet is printed like by lines, north, south, like little bent magnets like this. And then as you go across the sample, and sorry, Leo and Vicky, in your case, horizontal or across the sample in a different way, then it should be bumpy that way. So yeah, and actually, yeah. So I think theoretically, yeah, if you look really closely, it should be printed sort of in that similar fashion. But I think we're supposed to not tell, we're supposed to not give that away. But yeah, okay. Does anyone have any questions on this so far? Were they able to figure out the orientation of their magnet? I'm sorry that there's mixtures. I'm very surprised by that. Okay. Oops. All right. Now, this is to mimic. Again, we're using models, right? Lots of models because you cannot visualize anything very easily with this particular program. But it's supposed to mimic that same force microscope that I was talking about just earlier, right? So we have the scanning probe microscopy where we have this tiny, tiny tip that scans the surface of your sample, just like we did with the magnet. And then it can feel using different types of forces, either using physical force or electrical force, all sorts of different types of forces to feel the surface of the sample. I don't know if the slide will work. Nope, it will not work. But basically, it becomes an animation where you have this little tiny tip coming really close and then feeling the surface of your sample. And you can feel the bumps, you can feel an atom, and then it gets obviously projected onto the screen as it gets detected. All right, okay. And again, this is kind of similar. We're gonna take a look at atomic force microscope later today. But with that, I think I'm gonna hand it over to Miss Karithika.